Try looking back at this scene honestly. You're sitting inside a Boeing 777 that weighs nearly 300,000 pounds, a solid metal block nearly 64 meters long, tens of centimeters thick, filled with fuel, luggage, people, and it's not falling. It's gliding through the air at 900 kilometers slash, held up by air, a substance so thin you can wave your hand right through it, and yet it lifts what is essentially a small running building. These should shock you, should make you rethink your entire understanding of how the world works. But no, we're so used to it that we treat it as obvious. Then you're taught a few stories about why airplanes fly. The air above goes faster to catch up with the flow below. The curved wing creates lift. Bernoulli explains it all. Sleek, simple, clean explanation. And wrong. Not entirely accurate, but acceptable for now kind. I'm talking about wrong to the point that if you rely on them to understand how airplanes actually fly, you will completely fail. You'll hit a dead end. You'll ask questions that can't be answered because your foundational understanding is built on a beautiful story, but a wrong one. So before we go any further, I want you to brace yourself. What you're about to hear will contradict many things you thought you knew. Not because the world is deceiving you, but because nature has no obligation to look neat and tidy for your convenience. It just does what it does. And we, the curious ones who want to understand, have to learn to keep up with it. Come with me as we start dismantling every familiar myth about why airplanes fly. And let me warn you up front. You might not like what I'm about to point out, but afterward, you won't be able to look at an airplane wing the same way again. Now, let me tell you the story that virtually every textbook from the 1930s to the 2000s repeated like a mantra. It goes like this. Air splits at the leading edge of the wing. One part goes underneath along a shorter path. The other part goes over the top along a longer path, because the top path is longer. The airflow must speed up to meet the bottom flow at the trailing edge at the same time. And because of the higher speed, according to Bernoulli's principle, the pressure drops, and that pressure difference creates lift. It sounds very smooth, very logical, very clean. But it's wrong. And it's wrong right from the first assumption. I always laugh to ask equations that seems no one ever stopped to think about. Who ordered the two airstreams to meet up at the same time? Do they wear watches? Is there some invisible traffic cop finding them if they're late? There is no physical law, no equation that requires the two streams to reunite simultaneously. It's an assumption invented for convenience, then repeated so often that people forgot it. It was never proven. When researchers at the MIT Smart Visualization Lab in 1963 or NASA Glenn in 1999 actually observed the airflow around an airfoil, what did they see? They saw the upper flow reaching the trailing edge 2 to 5 times earlier than the lower flow. There was no reuniting on schedule. The upper air left the lower air in the dust like an Olympic sprinter racing a slow-walking uncle in the park. Path length doesn't force anyone to speed up. The flow speeds up due to a pressure difference, due to being bent by the wing shape, due to circulation appearing, not because it's politely trying to arrive on time. I often joke like this. If you and I walk around a building, me on the left, you on the right, do you think we have an obligation to meet back up at exactly the same moment? Nature doesn't operate on New York appointment schedules. The next thing that demolishes the equal transit time model is the symmetric airfoil. Aerobatic planes like the Pitts Special S2, Extra 300, or Sukhoi Su-29 use wings that are 100% completely symmetric. If equal transit time were correct, these planes couldn't generate lift at zero angle of attack, but in reality they generate massive lift just by angle of attack. You tilt the wing, you deflect the flow downward, and the flow pushes you up. No long path, short path at all. And if that's not enough to convince you the old theory is fundamentally wrong, look at the FA-18 Hornet, BAE Hawk, or Su-27. They fly inverted for minutes at a time. According to equal transit time theory, inverted flight should be impossible because the top path, now the bottom surface, is no longer. But they still fly, because lift doesn't come from that longer path. It comes from adjusting the angle of attack to deflect the flow downward. What about the simplest thing? Paper airplanes. Just a thin, flat sheet of paper, completely flat, no curvature, no camber, and it flies. Experiments from Stanford's PGL lab in 2016 showed a flat plate at 8 degrees AOA producing linearly increasing lift, completely shattering models based on curvature and longer paths. If a 6-year-old kid can fold a sheet of paper and accidentally disprove 80 years of textbooks, maybe we need to revisit the textbooks. And finally, CFD simulations from 2005 to 2020 ultra-high-resolution simulations run on supercomputers produced velocity fields completely different from equal transit time. No reunion, no speed up due to path length obligation. None of the cute simplifications generations were taught. Nature doesn't follow that story. And the most interesting part is, this isn't Bernoulli's fault. Bernoulli is still as correct as he was in 1738. The error is the wrong assumption we shoved into the equation, turning it into a beautiful explanation that doesn't reflect reality at all. If you start to grasp this, you're stepping into the real world of aerodynamics, more complex, messier, but also far more beautiful. And if you think only airplanes are haunted by wrong explanations, let me tell you one of the most famous myths in popular science. According to physics, bumblebees can't fly. This story started around 1934 when French physiologist Antoine Magnin and mathematician engineer André Saint-Pélague tried to apply fixed-wing lift equations to a bumblebee. They treated the bee's wings as small fixed airfoils moving through steady airflow. With that model, the calculations showed lift far too low to support the bee's body. Thus, the shocking conclusion was born: flight is impossible, at least according to physics. It sounds dramatic, sounds fascinating, and most importantly, sounds very shareable, but it's wrong from the root, and wrong in a way that makes me want to laugh. Because if you use the wrong formula, the only thing you prove is that the formula is wrong, not the bee, not physics, but that you're using a model that's completely mismatched to describe something entirely different from what the model was designed for. A bee's flight mechanism is nothing like an airplane's, not even close. Their wings aren't fixed airfoils like you see on a Boeing 777. Bees don't glide through the air. They flap, beat, rotate, fold, creating a series of highly non-linear aerodynamic effects you'd never see on a modern airplane wing. In 2005, biologist Michael Dickinson at Caltech published groundbreaking research on the flight mechanism of bees and similar insects. The data showed bees flap their wings about 230 times per second, an unimaginable rate for such a small creature. And with each flap, they generate a leading edge vortex, a stable vortex tightly bound to the leading edge, creating an extremely low pressure region above. Without the levee, bees couldn't fly. Without delayed stall, bees couldn't fly. Without rotational circulation appearing at the end of each flap, bees also couldn't fly. Look at high-speed camera footage, and you'll see the bee wing pulling the air, spinning it, distorting it, then exploiting that very vortex to generate lift. None of this mechanism resembles what you've seen in textbooks when they try to explain Bernoulli with drawings of two air paths splitting and meeting again. And right here, we need to say something important. Bernoulli isn't wrong. Bernoulli has never been wrong since 1738. What's wrong is the way humans chopped it up, distorted it, and crammed it into a story so simplistic. It no longer relates to reality. Bernoulli's principle holds for steady, irrotational, inviscid, weakly, nonlinear flow. But real wings have everything Bernoulli doesn't want to see. Viscosity makes air stick to the surface. Boundary layer makes velocity change dramatically within a few millimeters. Circulation makes the flow rotate around the wing in ways completely beyond the two streams meet assumption. So Bernoulli can't be used to predict velocity. It can only be used to calculate pressure once velocity is already known from other equations. Or in other words, Bernoulli is a consequence, not a cause. And this was clearly pointed out in a very famous 2010 NASA Glenn Research Center report titled Incorrect Lift Theories. NASA pointed out that the problem isn't Bernoulli. that the unverified equal transit time assumption 1 that was copied into textbooks for decades. So if you want to take a lesson from the bumblebee story, remember this. No formula is inherently wrong. Only humans use it wrongly. Nature has no obligation to obey the simple models we like. And our job isn't to force nature to fit the pretty story in our heads, but to look at nature and accept its wondrous complexity. But if the wrong stories about Bernoulli and bumblebees have shaken your faith a bit, this is the moment I bring you back to one of the simplest, most fundamental, and most overlooked laws in the entire history of aerodynamics teaching, Newton's third law. Yes, the thing you learned in middle school. For every action there is an equal and opposite reaction. Nothing mystical. No longer path. No two airstreams having to arrive on time. Just force and reaction force. And it explains most of the story of why airplanes fly. If you need a simple experiment to feel this, do the following. Next time you're in a car going about 60 miles per hour, that's nearly 96 kilometers, late 96 kilometers, stick your hand out the window. Hold your hand flat into the wind. Then tilt it up a little. Immediately you'll feel a force pushing your hand up. Tilt it down. Force pushes down. Tilt it against the wind. You feel the airflow being pressed somewhere by you. Nothing illustrates it more clearly than your own hand. When you tilt your hand, you push the air downward. And because you do that, the air pushes you upward. Simple, direct, and perfectly in line with Newton's third law. That's lift. And you just created it without needing a curved wing. Bernoulli or any other romantic story. Now scale that image up to the size of a real airplane. The engines don't just push the plane forward. That forward speed makes the wings sweep through the air, continuously deflecting the airflow downward. The entire mass of deflected air creates a momentum change. And per Newton, if the plane changes the air's momentum downward, then the air must push the plane in the opposite direction, upward. That's lift at its most primitive level. But let's get specific, because I like giving real numbers so you can see nature doesn't just like Newton, it obeys Newton down to the numbers. Behind a cruising Boeing 747, you can measure downwash the downward pushed airflow at velocities around 30 to 65, or about 9 to 18 meters per second. A gigantic mass of air is continuously pulled downward, as if the sky itself is being dented downward by the airplane. And if you still doubt the power of that momentum, listen to this. Wake turbulence. The downward vortices created by a large plane like a 747 or A380 can be strong enough to flip a small Cessna upside down within a radius of nearly 1 kilometer behind the flight path. The FAA mandates minimum separation distances between aircraft precisely because of this effect. That's not a concept. That's Newton in real life. All that downward pushed air is the clearest physical evidence that to keep a hundreds of tons object aloft, you must throw downward an amount of air equivalent to the object's weight every second. The faster you throw it down, the stronger you're pushed up. The less you deflect the flow, the smaller the lift. No miracles. Just momentum, velocity, and bent flow direction. And when you look at the problem this way, you'll see what centuries of debate over longer air paths completely missed. Airplanes don't need two airstreams to meet again. Airplanes need to push air downward. That's the wing's job. And if you forget everything else in this video, remember just one sentence. If you push air downward with exactly the weight of the airplane, the air will push you upward with exactly that force. No poetry needed. No myths needed. Just Newton. And the funny thing is, this has been true since 1687. But sometimes the most basic thing is the one overlooked the longest. Now, we have enough foundation to answer a more interesting question. If Newton explains most of the lift, then what's really happening on the upper surface of the wing, where 2/3 of the actual lift is generated? But to truly feel Newton at work in the sky, you have to look at a phenomenon that pilots respect, engineers approach with caution, and physicists regard as the undeniable signature of lift. Downwash, or more specifically, wake turbulence, the massive trail that an airplane leaves behind in the air. If you could see the air, you would witness a bizarre scene. The entire sky behind the airplane appears bent downward. Not just a little, not a few meters, but a strip 4 to 8 kilometers long, twisted into two gigantic vortices, spiraling downward like invisible tornado columns. That is weight turbulence. That is the footprint of lift. And that is the clearest Newtonian evidence you can observe in nature. When a Boeing 747 or Airbus A380 glides across the sky, it doesn't just pass through the air, it redistributes the momentum of an entire vast region of sky. The air is pushed downward, and since air cannot disappear, it reacts by swirling back, rolling into itself, forming violent vortices strong enough to persist for minutes. FAA studies from the 1970s to 2005 measured that the wakes of heavy aircraft can maintain vortex velocities large enough to be hazardous at radii of several kilometers. Some vortices even retain stable structure for up to 3 minutes, twisting deep into the space below the flight path like two giant air snakes. And this is why the FAA mandates separation times between aircraft during landing. If you let a Cessna 72 enter that wake, the vortex can flip it upside down in half a second. Not because the small airplane is weak, but because the amount of momentum the large airplane threw downward is so enormous. This is exactly what the longer path model can never explain. Because if lift came only from the air above going faster to catch up with the flow below, then behind the airplane nothing special would happen. There would be no reason for 2 kilometers long vortices to appear. No reason for the air to spiral downward like water draining in a bathtub. No reason for a 747 to create an effect strong enough to toss another airplane around. Yet every pilot knows wake turbulence is terrifyingly real. That can only happen when the airplane is pushing a gigantic mass of air downward every second. And it is precisely that downward pushed air that reacts by pushing the airplane upward. That is lift. When you look at downwash, you are looking at the visible to the eye version of Newton's third law. But let's go deeper. In physical terms, lift is not a miracle. It is downward momentum flux, the rate at which the airplane transfers momentum downward to the air. You change the air's momentum in the downward direction, and the air must produce an equal upward force. The simple formula, lift equals h times where is mass flow rate. And net v is the change in vertical velocity. A cruising 747 generates lift on the order of 700,000 to 800,000 newtons. That means it must throw downward an equivalent amount of air momentum every second. Air deflects down, the airplane deflects up. Nature doesn't care which path is longer. It only cares that momentum is conserved. And here's the interesting part. Downwash is not just a consequence of lift. It is evidence of lift. It is the fingerprint that any airplane leaves in the sky to prove it is exchanging momentum with the environment. If there is lift, there is downwash. If there is downwash, there is wake. Without deflected airflow, no airplane flies. When you see two trails of vortices stretching kilometers behind the large airplane, you are looking at a portion of the sky that has been bent by those very wings. And when you understand that, you realize lift is not something born from a pretty story in a textbook. It is the product of a powerful, raw, energetic physical process, one that Newton would instantly recognize if he stood beside the runway. So if downwash explains why airplanes have lift, then what explains why most of the lift comes from the upper surface of the wing, not the lower? If downwash shows you how dramatically the sky is bent, then angle of attack, the AOA, will show you what started it all. And the interesting thing is, you don't need a curved wing, no sophisticated aerodynamic shape, no complex structure. You just need to tilt a little. That's all. This was proven more than a century ago, in 1901-1902, when the Wright brothers built one of the world's first wind tunnels to figure out what really creates lift. They tested every wing shape, every camber, every size, and ultimately discovered something many later textbooks overlooked. Angle of attack is the single most important factor, so important that it often determines whether an object can fly at all. In their wind tunnel, flat plates, yes, just flat plates, no curvature, no airfoil at around 10 degrees AOR, produced lift coefficients of 0.8, a surprisingly large number for such a simple structure. What does this mean? It means you only need to tilt the wings so it deflects the airflow downward, and per Newton, the airflow deflects you upward. End of story. You don't need a longer path on top. You don't need airstreams reuniting on schedule. You don't need fancy-sounding myths that aren't true. You just need to tilt. When you change the wing's angle relative to the flow, you change the entire path the flow must take. The flow is forced downward. Pressure on top decreases. Pressure underneath increases. Enough lift appears. It all starts with one simple action, tilting the wing a bit. And this is what made the Wright brothers' experiments the foundation of all modern aerodynamics. But if flat plates can generate lift so well, then why do curved airfoils exist? Curved airfoils are indeed more efficient. They help the flow stay attached longer before separation, reduce stall, produce more lift at low angles of attack, and optimize performance. But curvature is not a necessary condition. It is only a condition that makes things better, smoothen, more stable. Like wearing better running shoes lets you run smoother, but you can still run barefoot. A flat plate at a reasonable AOA still flies. A curved wing flies more efficiently. If anything deserves to be called the core of lift, it is AOA. Look at real-world examples. Paper airplanes, almost always flat sheets. As long as they are launched with the proper AOA, they fly far, glide beautifully, and sometimes surprise you. Or aerobatic planes, like the Extra 300 or Pitts S2, which often use 100% symmetric airfoils. They don't rely on camber to generate lift. They use AOA and deflect the flow so strongly that they can fly straight up, inverted, spin, without needing traditional airfoil shapes. If camber were the only secret, these planes wouldn't exist. And to make the role of angle of attack even clearer, remember that a Boeing 737 during takeoff typically needs an AOA of 12 degrees to 15 degrees of value, very close to the Wright brothers' 10 degrees experiments from 1901. Technology changes, materials change, engines change, but AOA remains king. And this also explains why stall happens when AOA gets too large. You don't remove the camber from the wing, you just tilt it to the point where the flow no longer follows the surface. The boundary layer separates, the flow becomes chaotic, and lift collapses. AOA too small, not enough lift. ROA just right, optimal lift. ROA too large, loss of lift. The world of lift can be complex, but its key is so simple that children accidentally discover it while playing with paper airplanes. If AOA is the foundation of lift, then what causes most of the lift to come from the upper surface of the wing, where the low pressure is strongest? The answer lies in what the airflow does when it is forced to follow a curved surface, and in the way the flow accelerates according to a logic that human intuition often fails to grasp. So, if all it takes is tilting the wing to create lift, why in reality do 2/3 of the lift come from the upper surface rather than the lower? This is the point where many people get confused or cling to wrong explanations like the air on top has to go faster to catch up with the bottom. But when you look at real data instead of pretty stories, the picture is completely different. One of the most important documents on pressure distribution around airfoils is a NACA report H34, published in 1945. This report directly measured pressure at many different points on airfoils at various angles of attack, and found what anyone in aerodynamics today knows. Most lift does not come from air being pushed down on the lower surface, but from a powerful low-pressure region on the upper surface. To put it briefly, the air on top is accelerated more strongly, pressure drops more deeply, and it is this low-pressure region that pulls the wing up far more than the lower surface pushes it up. This may sound counterintuitive, especially if you only think in terms of Newton 3. But nature doesn't operate according to a single description. It uses all the equations we have, Newton, Bernoulli, Navier-Stokes, and even geometric flow effects that intuition struggles to picture. Looking at the pressure plots in NACA 824, you will see this characteristic repeated across almost every airfoil. The upper surface pressure line plunges like a steep cliff right after the leading edge, then gradually rises toward the trailing edge. The lower surface has only moderate high pressure, with little variation. The difference between the two surfaces, the strong negative pressure on top versus the mild positive pressure below, creates most of the lift. But the real question is, why does the upper airflow accelerate so much? And this is when you must abandon the image of air being sucked, because it takes a longer path. Air has no reason to care about path length, but it is forced to change direction when it encounters the airfoil shape. This is called streamline turning. The streamlines are bent to follow the airfoil contour. A flow that is curved must change its momentum in the direction of that curve. And in flow, when you bend the streamlines downward aft, you're forcing the upper flow to cling to the wing surface, thereby requiring it to accelerate to maintain continuity. Imagine sweeping your hand quickly across a lake surface, curving downward. The water above your hand gets pulled along and speeds up, not because it knows it has to arrive on time, but because your hand shape forces it to. An airplane wing does the same to air. Curvature plus streamline turning is the powerful duo that explains this. The curved shape on the upper surface creates an environment where the flow must turn more sharply than on the lower surface. To turn, the flow must increase velocity. When velocity increases, pressure decreases, a consequence of Bernoulli's equation along a streamline, once actual velocity is known from Navier-Stokes equations. And when pressure drops more sharply on top, most of the lift is generated there. No need for two air streams to meet. No need for a longer path. Just the airflow being forced to do what air naturally does when meeting a curved obstacle. Cling to it, accelerate, reduce pressure. This also explains why curved airfoils perform better than flat plates. The curve helps the flow stay attached longer, separates less, and keeps the low pressure region extended farther along the cord. And that very low pressure region generates a great deal of lift. When you look at NACA 824 data, you see clearly that lift is distributed roughly as follows. The lower surface contributes about 1/3. The upper surface about 2/3. This is fully consistent with both experimental data and modern CFD simulation. To see this with your own eyes, just look at Schlieren videos or smoke visualizations. The upper flow is pulled tight and visibly accelerates, while a lower flow remains relatively straight and slower. And one more important point, the upper flow carries bound vorticity, which plays a major role in sustaining lift. Curvature, streamline turning, and circulation combine into a complete system complex, non-linear, full of surprises, but all leading to the same conclusion. The upper surface is where the real magic happens. You can push air down to make the airplane fly, but to push air down really efficiently, you need high velocity on top, low pressure, and strong attachment between the flow and the wing surface. That's where the entire secret hides. And once you understand this, you see why all oversimplified models fail. They ignore the foundational role of the upper flow, something not just important, but decisive for the majority of lift. But the story doesn't end here, because to truly understand why the flow stays attached to the wing, why it doesn't separate immediately, why it tolerates bending without saying, "I give up," we must enter the world where air shows its sticky, lazy, but powerfully strong nature. And that is when the no-slip condition steps onto the stage. But to understand why the airflow is willing to bend according to the wing shape and create a powerful low-pressure region on the upper surface, we must touch on one of the most important properties of fluids of property. So simple, it's often overlooked, yet so powerful, it dominates the entire aerodynamics of flight. The no-slip condition. This condition states that at the surface of any solid object, the velocity of the fluid relative to that surface is exactly zero. Not approximately zero, not nearly zero, exactly zero. This sounds absurd if you've never seen Osborne Reynolds' 1883 experiment, where he pumped dyed fluid through a glass tube and discovered that right next to the tube wall, the flow does not slide. It stands still. It's stuck to the surface, and the subsequent layers of fluid must slide over the layer next to the wall. The farther layers slide over the inner ones, creating a shear gradient, a velocity gradient that increases gradually from zero at the surface to the free stream velocity farther away. That is viscosity. And it is precisely viscosity, a thing that many simplified explanations of lift pretend doesn't exist. That is the core reason the boundary layer forms. Look at this simple but crucial truth. Airflow never slides freely over an airplane wing. It is held back, dragged, retarded, forced to go along with the wing surface for a distance. The air right at the surface must go slowly. The air layer above must go faster to compensate. And the farther from the surface, the closer the velocity gets to the main flow velocity. This is the velocity structure we call the boundary layer, a thin layer only a few millimeters thick, yet with the power to determine the entire way the airflow interacts with the wing. Without it, there is no lift, no stall, no wake, no airplanes as we know them today. Try imagining air as layers of stacked cards. The bottommost layer, the one touching the wing, is held firmly and cannot move. The layer above slides over it. Then the next layer slides over the one below, all forming a velocity gradient. This is exactly the no-slip condition in action. Air isn't water, but fundamentally it does the same thing. It doesn't slide freely over surfaces. And from that comes an extremely important consequence. If the wing is curved downward, the air right at the surface is dragged along, and the layers above, bound by the shear gradient, must also curve. The air has no other choice. It is stuck to the wing. And that is why the airflow can accelerate so strongly on the upper surface. It is pulled along by the very motion of the surface and the curvature shape of the wing. Not because of path length, not because of any mysterious reason. Because the no-slip condition forces it to do so. This simple condition also explains why stall occurs. When the angle of attack is too large, the boundary layer no longer has enough energy to stay attached to the curved surface and separates. At that point, the airflow no longer follows the wing shape. The low pressure collapses, lift vanishes. Simple, logical, no magic. If you look at the boundary layer through Schlieren cameras or modern CFD visualizations, you'll see it resembles a blanket of air covering the wing, oscillating, vibrating, changing thickness every centimeter, but always obeying the same fundamental principle, no slip. And one more factor, because the air layer right at the surface is slowed down, it causes friction and produces drag, but at the same time, it allows the upper airflow to know there is a solid surface beneath it, and that surface is moving in a certain direction. Without shear, there is no interaction. Without interaction, there is no lift. This may sound like a minor detail in fluid physics, but it is the very foundation upon which all of aerodynamics rests. You can rewrite Bernoulli's equation. You can ignore circulation. You can argue about Newton or Navier-Stokes. But if you ignore the no-slip condition, you will never understand why airplanes fly. And when you accept no slip, you must accept the boundary layer. And when you accept the boundary layer, you must accept that airflow can separate, can attach, can accelerate, can decelerate. And all of those determine whether the airplane generates lift or not. No slip is not a side detail. It is the silent narrator of the entire flight mechanism. But to see the full power of the boundary layer, we must look at the historic moment when this idea emerged, shaking aerodynamics to its core and paving the way for everything from airplane wings to modern gas turbines. That is the story of Ludwig Prandtl, and it happened in 1904, one of the most important years you were never told about in class. And so we arrive at one of the greatest moments in the history of aerodynamics, a moment that almost no student is taught with the proper sense of its importance. Yet it is the foundational brick for everything from airplane wings, jet turbines, to the swirling vortices you see out the airplane window. In 1904, at the International Congress of Mathematicians in Heidelberg, a young engineer named Ludwig Prandtl took the stage with a paper of just 8 pages. Yes, 8 pages. So short that many contemporaries dismissed it. But in those 8 pages, Prandtl introduced a deceptively simple idea that was powerful enough to change the entire field of aerodynamics. The flow does not truly stick to the entire body only. A thin layer right at the surface matters, and that layer is what determines lift, drag, and everything else. He called it the boundary layer. What sounds minor turned out to be a revolution. Before Prandtl, the world tried to explain aerodynamics with beautiful, clean, frictionless, inviscid Euler equations, a world too idealized to describe any real airplane. Mathematicians calculated perfect flow around perfect bodies, and the results were always beautiful and completely wrong compared to the real world. You know the story. D'Alembert even proved that a body moving through an inviscid fluid would experience exactly zero drag and zero lift. A mathematically correct conclusion, but wrong in nature, and Prandtl was the first to explain why. Because all the messy energy of the flow is not in the large mass of air outside. It is in the few millimeter thin layer of air right at the surface. And in this layer is so thin you might think it's unimportant. Viscosity, the stickiness, exerts its absolute power. A few millimeter thin layer of air decides the fate of the entire flight. It is in that boundary layer where velocity rises from zero to the free stream value. It is there that the flow attaches, slips, accelerates, decelerates, and sometimes when treated too harshly separates from the wing surface. This separation, boundary layer separation, is the culprit behind stall one of the most important and dangerous phenomena in aviation. When AOA is too large or when the wing surface no longer gives the boundary layer enough energy to follow the curve, this layer rebels by peeling off, rolling up, creating a chaotic high-pressure region on the upper wing. And since we already know that 2/3 of lift comes from the upper surface, this loss of attachment causes lift to drop suddenly. The airplane pitches, sometimes falls freely, all because a few millimeter thick layer of air no longer wants to cooperate. What is astonishing is that before Prandtl, no one had the conceptual tool to describe this. People knew stall happened but didn't understand why. People saw flow separate but didn't know the origin. And people kept thinking Bernoulli explained everything without realizing Bernoulli only holds when the boundary layer doesn't separate. See, only when you understand the boundary layer do you understand why Bernoulli is correct under some conditions and absolutely wrong under many others. Only then do you understand why the streamlines over the airfoil must curve, why velocity increases, why pressure drops. You understand why airfoils with reasonable curvature resist stall better, and why flat plates stall quickly, even though they can still generate good lift at small AOA. Everything suddenly becomes clear when you look through Prandtl's eyes. It's not the entire flow that matters, but this thin layer. And it doesn't stop there. The boundary layer also explains drag, wing efficiency, control authority, even airplane stability in turbulent air. Remember that when you look at the 8-kilometer-long wake turbulence behind an airplane, you are looking at the consequence of boundary layer separation and rolling up into gigantic vortices. You are looking at the signature of the boundary layer at work. Put another way, without the boundary layer, there is no aerodynamics, no airplanes, no turbines, no flow we can describe. Accepting Prandtl's idea didn't just change aerodynamics, it gave birth to aerodynamics. The Navier-Stokes equations are no longer too alien or inexplicable. They become meaningful because Prandtl showed us where in the real flow really matters and where is just idealized passing by. And when you have the boundary layer, you have an indispensable piece, the story of lift's existence in viscous flow, the story of circulation, of the starting vortex, or what Euler and Bernoulli could not explain. To fully understand lift, you must pass through the door Prandtl opened in 1904. And after passing through, you can never go back to oversimplified explanations again. But the boundary layer is only half the story, because to have sustained lift, it's not enough for the air layer to stick to the wing. You also need a special vortex structure, a kind of imprint that any lift-generating body carries with it. But before we move on to the starting vortex, the heart of the lift story, we must go back to one of the most famous puzzles in the history of fluid physics. A puzzle that baffled the scientific world for nearly 2 centuries, D'Alembert's paradox, presented in 1752. It is a paradox born from the deadly beauty of ideal mathematics, and if you've ever heard someone say, according to theory, airplanes cannot fly, most of the problem lies here. The paradox states that a solid body moving through an inviscid steady fluid will experience exactly 0 drag force and 0 lift force. No drag. No lift, no net directional pressure force, nothing. It's as if the body is moving through absolute vacuum. And here's the issue. The Euler equations for inviscid flow completely agree with this. Mathematics is very happy with that result. Beautiful, symmetric, clean, no messy complications. But reality doesn't care about mathematical beauty. Put a real object in the window brick, a ball, an airplane wing, and you'll see drag appear immediately. Put an airfoil at positive angle of attack, and you'll see lift appear immediately. In reality, every flow around a solid body produces drag, and if the shape is right, produces lift. But the ideal Euler equations insist that none of this exists. This contradiction left 18th and 19th century scientists utterly perplexed, not because they didn't believe experiments, but because they lacked the language to explain why their beautiful equations gave a result completely opposite to the real world. Some tried to patch it by saying there must be some mysterious force, but no one knew where it came from. And for decades, aerodynamics was stuck in a kind of developmental dead end. If your foundational equations say lift doesn't exist, you cannot build a correct theory of aerodynamics. And that is exactly the point where Ludwig Prandtl broke through. He showed that the problem wasn't in the mathematics, but in the over-idealized assumptions. Euler was describing a world without viscosity, a world where the no-slip condition doesn't exist, a world where flow doesn't stick to bodies, doesn't create shear, doesn't create boundary layers. In other words, Euler was describing a universe unlike anything that exists in real life. And in that ideal universe, yes, you have no drag and no lift. Not because lift is impossible, but because the modeling assumptions eliminated every physical mechanism that creates lift from the start. Imagine trying to describe car motion but assuming zero tire friction. You would conclude the car cannot turn, and you'd be correct in the model, but completely wrong in reality. That is precisely what happened to aerodynamics before 1904. When Prandtl introduced the boundary layer, he didn't just explain drag and stall, he shattered D'Alembert's paradox and reconnected aerodynamics to the real world. In the few millimeter thin boundary layer, viscosity cannot be ignored, shear cannot be ignored, momentum transfer cannot be ignored, and when viscosity enters the game, everything Euler said about drag equals zero vanishes like smoke. Not only does drag appear, but lift appears too, because the boundary layer in no-slip condition forced the upper airflow over the airfoil to accelerate strongly, creating a low-pressure region. All of this was hidden from Euler because he worked with a viscosity-free model. If you remove viscosity from the equation, you've removed the very thing that makes physics work. You can view D'Alembert's paradox as a powerful reminder of the danger of over-idealized models. If you make the world too perfect, you kill the real mechanism that operates it. And airplanes are the clearest proof of that. They fly not in Euler flow, but in Navier-Stokes flow, which includes viscous terms, shear stress, and boundary layers. When you accept viscosity, you accept reality. Lift is the product of nonlinear, viscous, vortex-filled flow, where the boundary layer and circulation are the main characters. When you remove viscosity, you return to a clean but unreal world where airplanes cannot fly. But this paradox did one more thing. It paved the way for the next question. If lift belongs to the viscous world, then what mechanism creates circulation? What creates the bound vortex around the wing that helps the flow stay attached and accelerate? And how does a moving body spontaneously generate that vortex structure in the flow? And so we come to the strangest but most important moment in the entire process of lift formation, the starting vortex, which occurs the instant the wing begins moving through the air. If the boundary layer is the heart of aerodynamics, then the starting vortex is the flip of the switch that makes lift appear and stabilize. Without the starting vortex, you never get bound circulation. Without bound circulation, you have no powerful low-pressure region on the upper surface of the wing. Without the low-pressure region, you have no lift. Everything is tightly interlocked like gears in an intricate machine that nature designed billions of years ago. To understand the starting vortex, we must go back to 1869, when physicist William Thomson, better known as Lord Kelvin, formulated Kelvin's circulation theorem. Kelvin's theorem states that in an ideal inviscid flow, The circulation around any closed material curve is always conserved. But when you introduce a real wing into a viscous flow with a boundary layer, circulation is no longer forbidden from appearing. It can form and self-adjust, but it must always obey one crucial principle. Whenever circulation appears around the wing, there must be a corresponding vortex structure shed downstream. That is precisely the starting vortex. When the wing begins to move or when the flow speed around the wing suddenly changes, the boundary layer on the upper surface doesn't have enough energy to attach immediately. It gets rolled up and spirals into a large vortex behind the wing. This vortex rotates in a specific direction, and per Kelvin, if a vortex rotating in direction A is shed, there must be a circulation rotating in the opposite direction, A, appearing on the wing. The starting vortex is the shed vortex, and the bound vortex, the vortex bound around the wing, is its twin, but opposite counterpart. No starting vortex, no bound vortex, no lift. This was once just beautiful theory, but by the 1990s, visualizations at the University of Illinois captured the phenomenon spectacularly. When they introduced thin smoke around an airfoil and accelerated the flow, you could clearly see the starting vortex form. A large swirling ring detaches from the wing and is carried downstream by the flow. Almost immediately after that moment, virtually instantaneously, the flow around the wing reorganizes, forming a stable circulation with streamlines clinging tightly to the upper surface, accelerating, producing pressure, and beginning to generate steady lift. That is when the bound vortex appears. The starting vortex is like the spark. The bound vortex is like the lamp that has been lit and continues to burn steadily as long as the wing is in motion. When the airplane reaches steady speed, the starting vortex departs forever, but the bound vortex remains, continuing to sustain circulation. And the bound vortex is exactly what pulls the upper streamlines down toward the wing surface, accelerates them, and creates a stronger low-pressure region. It is the reason Bernoulli hold along streamlines, because the velocity you see on the upper surface is a consequence of circulation, not merely the curvature shape alone. Imagine swirling a spoon in a cup of water. Each time you swirl, the water rolls into a vortex. When you stop swirling, the initial swirl is shed away, but the remaining swirl in the cup continues to rotate slowly, creating a bound rotation around the spoon. The starting vortex is the swirl thrown outward. The bound vortex is the swirl that stays around the object, and the two must exist as a pair. That is why lift is not just a matter of airflow bending downward, or pressure dropping on the upper surface. Lift is the result of an organized vortex system, where the starting vortex initiates the process, and the bound vortex sustains it. No starting vortex, no bound vortex, no bound vortex, no streamline turning, no streamline turning, no flow acceleration, no low acceleration, no low pressure, no low pressure, no lift. A perfect logical chain. This also explains why every airplane leaves kilometers-long weight turbulence behind. The starting vortex and its offspring vortices are carried away by the flow, forming two gigantic downward rolling vortices, while the bound vortex stays with the wing to produce steady lift. And what is astonishing is that the entire formation of the starting vortex occurs in a fraction of a second. The wing only needs to start moving, and the vortex is born. No delay, no hesitation, no philosophical complexity. Just pure physics doing exactly what the Navier-Stokes equations require it to do. This is why every explanation that ignores circulation is only partially correct. The vortex system, starting vortex and bound vortex, is the foundation for any complete description of lift, from Newton to Bernoulli to Navier-Stokes. But circulation is not something that happens naturally. If you only look at shape, it is something created by the unimaginable interaction between the no-slip condition, viscosity, boundary layer, and the very motion of the wing through the air. That is where the true beauty of aerodynamics reveals itself. After seeing how the starting vortex gives birth to the bound vortex like twins pulled in opposite directions, we must ask, what exactly is the bound vortex? It is not the kind of whirlpool you see in a bathtub drain, not a visible tornado furiously spinning around the wing, and not a spiraling airflow as people often simplify in illustrations. No, Circulation is something subtler, more abstract, yet profoundly real. When you stand in a wind tunnel, it is the way velocity is distributed around the wing to produce a net vertical effect. In mathematics, circulation is defined by the formula Tho equals ng v dial, that is, you take a closed curve enclosing the wing, go around once, and sum up all the tangential velocity components along that path. If the total is not zero, you have circulation. Simple mathematically, but profoundly deep physically. But here's the issue. Many people see this formula and immediately imagine circulation as a real whirlpool, like pouring water down a drain and seeing it spiral into a funnel. But the bound vortex around the wing does not have that visible spiral shape. The airflow does not circle around the airfoil. It accelerates and deflects in a far more complex pattern. Circulation is an integrated quantity describing the net deviation of velocity, not the literal fact that air molecules are orbiting the wing like planets around the sun. If you stand in a wind tunnel with Schlieren cameras or smoke wire visualization, you won't see a complete vortex ring wrapped tightly around the wing. You will see streamlines bending, being pulled tight against the upper surface, accelerating strongly, then departing at the trailing edge. Circulation exists in that very acceleration and bending, not in any visible vortex structure. Imagine it this way. You run around a stadium and feel the wind on your face. If you run against the wind direction, you feel stronger wind. If with it, weaker. Circulation is like summing up all that deviation, integrated along a closed loop around the wing. It is like an invisible rotation, not because it doesn't exist in reality, but because it exists in the velocity field model, not in the physical shape of the flow itself. The bound vortex manifests circulation in this way. The airflow above the airfoil is faster than below. This creates a net velocity difference around the closed path, and that net is circulation. But circulation doesn't come from nowhere. It is activated by the starting vortex, sustained by the boundary layer, and stabilized by curvature and streamline turning. Another way to picture it, imagine a strip of paper tape wrapped around the wing, with wind blowing stronger on top, weaker underneath. If you record the speed at every point on the tape and sum it all up, you get circulation. Nothing is literally spinning, but the total velocity says there is a net vertical effect around the wing. That is what makes circulation special. It is not a force, not a vortex, not a flow stream, but a mathematical property of the velocity field, yet directly linked to lift. This is clearly proven in modern CFD simulations. If you strongly increase velocity on the upper surface without changing the lower, circulation increases. When circulation increases, lift increases. If you do the opposite, lift decreases. And if you remove curvature or angle of attack, circulation drops near zero and lift vanishes. Everything matches. Circulation is also not unique to airfoils. It appears in spinning baseballs, topspin tennis balls, bird wings, helicopter rotors, wind turbine blades. Any object that accelerates flow above and decelerates it below creates circulation. It is the common signature of every lift-generating system. And the interesting thing is that circulation does not contradict Newton or Bernoulli. It is precisely the bridge connecting the two seemingly opposing descriptions. When circulation accelerates the upper flow, pressure drops. When pressure drops, lift appears. At the same time, the flow is deflected downward, all perfectly compatible, no contradiction whatsoever. Those who try to turn Newton and Bernoulli into opposing camps simply don't understand circulation. Because when circulation exists, Newton is satisfied because there is downward momentum change. Bernoulli is satisfied because there is reduced pressure on top. And Navier-Stokes is satisfied because boundary layer and shear stress exist. In short, circulation is the mathematical bloodstream of the entire lift phenomenon. But we still need one more thing, a boundary condition that makes circulation not infinite, not arbitrary, but unique. A condition that forces the flow to lead the wing in one specific way, eliminating countless unrealistic mathematical solutions and keeping only the one that matches the real world. That condition is called the cutter condition. This is the moment we arrive at one of the most subtle yet extremely important principles in aerodynamics, the cutter condition. proposed by German mathematician Martin Wilhelm Kotter in 1902. If circulation is the quantity describing the net vortical strength around the wing, then the Kotter condition is the boundary law that prevents circulation from taking any value mathematics might allow. It forces the flow to choose only one exit path, the path that matches what we observe in reality. Without this condition, you would have a forest of mathematical solutions both flow around an airfoil, but only one of them describes the real world. The Kotter condition is what lets us find that correct solution. The core of the Kotter condition lies in a simple observation. The trailing edge of the wing is sharp. It is not arbitrary that airfoils are designed. This way, the edge is sharp enough that the flow cannot abruptly turn upward or downward at that point when leaving the wing. Air cannot change direction sharply at too small an angle without incurring enormous energy cost, unless forced to. Therefore, when the flow reaches the trailing edge, it must choose the most natural path, continuing straight rearward, smoothly, without sharp turns. Imagine driving and reaching an intersection where one path is a smooth curve, the other a tight 90-degree corner that makes your tires screech. Which do you choose? Air chooses the smooth path, the one with the least pressure gradient. The Kotter condition states exactly that. The flow leaves the wing at the trailing edge smoothly, without forming a sharp angle, without abnormal vortices. It sounds obvious, but it has a profoundly deep consequence. It determines circulation. Remember that circulation dessous is the line integral of velocity around the airfoil. Mathematics allows countless different velocity fields, meaning countless different dou values, all satisfying the Euler equations, but only one dou value makes the streamlines leave the wing smoothly. That value is the one nature selects. Circulation appears not because the curved wing creates it, but because the Kotter condition forces the flow to leave the wing in exactly one way. And circulation is the value that satisfies that requirement. This is the point that so many popular explanations overlook. Circulation is not something that arises arbitrarily. It is the unique solution that satisfies the viscous flow boundary condition at the trailing edge. If circulation is too small, the upper flow doesn't accelerate enough. Pressure doesn't drop enough. Streamlines cannot stay attached and leave smoothly. Instead, they reverse and create a mathematical singularity at the trailing edge. If circulation is too large, the flow is pulled too strongly upward, causing separation or flow distortion again, not smooth. Only one thou value makes the flow leave the wing as beautifully as we observe in wind tunnels. And it is this very sense of nature selecting the unique solution that makes the Kotter condition the bridge between mathematics and the physical world. Imagine you have a ribbon tied around the wing. Wind blows through, pulling the ribbon along. If circulation is wrong, the ribbon jerks wildly, turns up, turns down, twists at the trailing edge. But only when circulation is correct does the ribbon lie straight, leaving the wing smoothly, without spinning around. The Kotter condition is the requirement. Force the ribbon to leave the wing along a straight path. But to achieve that, the velocity field must adjust, and that adjustment is circulation. This is also why airfoils need a sharp trailing edge. If you round the trailing edge, air can split in two different directions without obeying the Kotter condition, and lift drop sharply. With a sharp trailing edge, nature has no other smooth escape route except to select the appropriate circulation. At this point, we have all the pieces: no slip, boundary layer, starting vortex, dawn vortex, dawn circulation, Kotter condition. A smooth chain of cause and effect, and here it is, the natural culmination of the entire journey from no-slip boundary layer, starting vortex, circulation, all the way to the Kotter condition. The Kotter-Joukowski theorem, published in 1906, one of the most beautiful, concise, and powerful formulas in the history of fluid physics. It states that the lift on a wing section per unit span length is exactly given by the expression L equals first T and B times V. No square roots, no rotation matrices, no 8-degree polynomials, just three parameters multiplied together. Simple enough to look like an equation you could scribble on the corner of your desk when half asleep. But beneath that simplicity lies the entire complexity of viscous flow. Boundary layer, streamline turning, circulation, and the Kotter condition. This expression wasn't casually pulled out of thin air by some mathematician. It is the result of synthesizing everything we've discovered in the previous 13 parts. The denser the air, higher, the more material the wing has to act upon, and every cubic meter of air the wing deflects produces more momentum change. Fly at high altitude in thin air, and you need a higher AOA or higher speed. Fly at sea level, and you get stronger lift for the same velocity in circulation. Density is the invisible lever everyone knows about, but few truly understand. The relative flow velocity over the wing. This is why airplanes must accelerate down the runway. Higher speed means more air mass interacting with the wing per second. Stronger momentum change, greater lift. But to understand V in the context of Kutta-Joukowsky, remember that it is circulation itself that determines the velocity distribution above and below the wing. V is only the initial free stream velocity. Thought, gamma, circulation, the net vertical strength around the wing. This is the true king of the equation. If circulation is zero, lift is zero. If flow increases, lift increases linearly. This is why an airfoil generates stronger lift than a flat plate at the same speed. The airfoil produces better circulation thanks to smoother curvature and streamlined turning, and because the Kutta condition forces circulation to reach the appropriate value. Circulation isn't something you want to have. It is something the flow must have to leave the trailing edge smoothly. And once circulation is determined, your lift is determined. No ambiguity. No intuition. All captured in a single multiplication. Let's try a real-world calculation to see that this formula isn't an intellectual game. It is real physics. Suppose we have phase A equals 1.225 kilograms lash Mach. Air density at sea level, V equals 70 miles, equivalent to 252 kilometers lash H. A typical low speed for a small aircraft. Thous requires 12 meters sways A, reasonable circulation value for an airfoil at moderate angle of attack. Plugging in, L equals 5 times B times O, 1225 times 70 times 12 and 12, 1225 times 70 times 12, and 1 means. Every meter of wingspan produces about 1,029 newtons of lift, equivalent to supporting roughly 105 kilograms per meter of span. If you have a 10-meter span wing, you're generating over 1 ton of lift just from circulation established correctly according to the Kutta condition. This isn't simulation. It isn't assumption. It is real, measurable, verifiable force. And here is the astonishing part. This formula matches thousands of experiments from NACA in the 1930s, 1950s to NASA CFD simulations in the 21st century. From paper airplanes to modern drone blower wings, from albatross seabirds to Apache helicopter rotors, every lift-generating system obeys this formula. It is the universal language of everything that flies. But the true beauty of Kutta-Joukowsky lies not in its accuracy, but in the elegance of the relationship it reveals. Lift is not a mystery. Lift is not magic. Lift is not two airstreams having to meet. Lift is the inevitable consequence of circulation established by the boundary conditions of real flow. You can describe lift with Newton, momentum change, with Bernoulli, pressure drop, with Navier-Stokes, velocity gradients and shear, or with circulation, though, but all converge at the same point. And that point is Kutta-Joukowsky. It is like the E equals mc squared of aerodynamics. Unbelievably concise, profoundly irreplaceable. But we're not done yet, because now you have 4 languages to describe the same phenomenon: Newton, Bernoulli, circulation, and Kutta-Joukowsky. And if you truly want to understand how airplanes fly, you must realize that these 4 languages do not contradict each other. They blend together like 4 instruments in the same symphony. And this is the moment we must confront a reality that generations of students, teachers, engineers, and even some scientists have missed. Newton, Bernoulli, and circulation do not contradict each other. No camp is more correct than the others. There is no philosophical war between downward push and pressure reduction, or between momentum change and though equals AO ik bik. These three descriptions are like three different instruments in the same symphony. If you listen to only one, you think you understand the piece. But when you hear all three, you realize the true sound is far richer and deeper. In physics, Newton is the melody, the main tune, most intuitive, easiest to grasp. The wing pushes air down, air pushes the wing up. Bernoulli is the harmony, the balanced pressure distribution that gives the smooth, continuous feel of flow. Circulation is the rhythm, the hidden beat, the net vortical structure you don't always see, but which keeps the whole system in time. Separately, each is correct. Together they form the complete picture of lift. Start with Newton. All lift must obey momentum conservation. Air pushed down, wing pushed up. The formula L equals times that O's in every case, every altitude, every speed. If you don't change the air's momentum, you have no lift. But Newton doesn't say how the air gets pushed down. He only says that if you push it down, you get pushed up. Bernoulli answers that question at the pressure level. When flow accelerates over the upper surface, pressure drops. Low pressure pulls the wing up. Higher pressure underneath pushes it. The difference creates lift. But Bernoulli doesn't say what makes the flow accelerate according to the wing shape. He only describes the consequence, higher velocity, lower pressure. Circulation explains why velocity is distributed that way. When flow appears around the wing, upper flow accelerates, lower flow slows and streamlines bend. That is what creates the pressure difference Bernoulli describes. All three layers fit together perfectly like the floors of a building. Newton is the ground floor. You can't fly without momentum change. Bernoulli is the second floor. You need pressure distribution for refined, stable force. Circulation is the third floor. You need the net vortical structure to keep flow attached and satisfy the cutter condition. No floor is truer than the others. They are just different viewpoints shining on the same single truth. Lift is the result of non-ideal flow around a moving body. Take an example. When you explain lift with Newton, the listener asks, but why is the air pushed down according to this specific curved shape? You need Bernoulli and streamline turning. When you explain with Bernoulli, the listener asks, but why does velocity change that way? You need circulation. When you explain with circulation, the listener asks, but where does circulation come from? You need boundary layer and starting vortex. When you explain boundary layer, the listener asks, but why is there a velocity gradient? You need viscosity and no slip condition. And when you explain viscosity, the listener asks, but why can't we just use Euler? You need D'Alembert's paradox. Everything connects like a tight network. No single model is comprehensive alone, but each model illuminates one part of the phenomenon. The funny thing is that many debates over decades were really just arguments between people clinging to one description as if it were absolute truth. If Newton is right, Bernoulli must be wrong. If Bernoulli is right, circulation must be nonsense. If circulation is right, Newton is just a low-priority explanation. But nature doesn't play pick a side. Nature just does what it does. We are the ones choosing models depending on the question we want to answer. You want intuitive understanding of why airplanes fly. Newton is the fastest way. You want to calculate surface pressure on the wing. Bernoulli is an excellent tool. You want to describe stable lift for any airfoil shape. Circulation and Koto-Joukowsky are the only path. Nature doesn't force you to choose one. Nature says, this is everything that's happening. Pick the tool that fits your question. That is the great lesson I wish more textbooks taught earlier. There is no most correct model, only the most useful model in a specific context. And when you learn to use all three languages of Newton-Bernoulli circulation, you don't just understand how airplanes fly. You understand how science itself works. Nature doesn't care whether your explanation is simple. It only cares about correctness. And sometimes, to see that correctness, you must layer multiple descriptions like instruments in an orchestra. But this journey isn't over yet. Because there is one more question you must face. If everything is so clear, why for decades and even today have millions of people been taught wrong models? Why does the equal transit time myth still appear in textbooks? And why is correcting it so difficult? If Newton, Bernoulli, circulation, and Kutty-Joukowsky describe lift so well, then why has a wrong explanation like equal transit time? The air on the upper path is longer, so it must go faster to catch up with the lower flow, persisted for over 80 years, infiltrating textbooks, museums, lectures, classrooms, and even some university curricula? The answer isn't in physics. It's in cognitive psychology. Humans, all of us, without exception, love neat, beautiful, fragrant, believable explanations. A simple story has near magical appeal. It gives us the feeling that we understand something complex without paying the intellectual price. And once a makes-sense explanation gets lodged in the mind, it is extremely hard to dislodge, even when it is blatantly wrong. Michael McCloskey's famous 1983 study on physics misconceptions showed this brutally. When he asked college students, even science majors, about motion force, inertia, many still believed in basic Aristotelian models. A force must exist for an object to keep moving. Even though they had studied Newton, passed Newton tests, and completed Newton courses, correct knowledge stayed for exams. Wrong knowledge stayed for everyday life. McCloskey called these intuitive misconceptions, mental models so deeply rooted they can't be dug out. And equal transit time is a sophisticated misconception. It doesn't look obviously wrong at first glance. It requires no math. It has a geometric logic appearance. It is beautiful. It is too beautiful. Beautiful enough to override experimental checks in the learner's mind. Once a beautiful explanation enters textbooks, especially popular ones, teachers start teaching it. Students hear it, believe it, later become teachers and teach it again. The error gets copied across generations like a fading photocopy that never disappears. What's worse, when someone points out it's wrong, those who believed it for years find it harder to accept, not because they're stubborn, but because the brain hates changing a stabilized mental model. It's like believing the sun orbits the earth your whole childhood. Then one day someone says the earth is the one orbiting. The new theory is correct, but the feeling is wrong. You don't feel the earth turning. You see the sun moving across the sky, and your brain trusts the feeling more than the math. Lift is the same. When you hear equal transit time, you think, makes sense. Longer upper path, faster treasure drop, lift. But you don't stand behind an airplane wing at 200 kilometers / to see that upper flow accelerates, not because of path length, but because of curvature and circulation. You don't see CFD pressure contours. You don't see the bound vortex rotating around the wing. You just see a nice drawing with two beautiful curved lines. And your brain loves that drawing. That's why textbooks keep using wrong models. Simplification. Not because they don't know the full model, but because they think students don't have time to learn the real one. So they choose the most plausible sounding model to teach. The problem is, a wrong but plausible model has stronger staying power than a correct but complex one. You see this everywhere in science. Electrons orbit like planets. Wrong. Mass increases with velocity. Oversimplification. Color is a property of the object. Wrong. In optical physics, centrifugal force is a real force, not etc. When a mistake gets packaged into a memorable image, it becomes nearly immortal. And equal transit time is the same. It survives not because it's right. It survives because it sounds right, looks right, feels right. But reality doesn't care about your feelings. Nature doesn't bother explaining itself in the most minimal way. Nature does what it does. And the job of science is not to provide a beautiful story, but a correct story, even if it's more complex, messier, harder to swallow. And the greatest irony, once you understand circulation, Kutty-Joukowsky, streamline turning, boundary layer, and the physics behind lift, you realize the correct explanation isn't harder to understand, it just wasn't taught properly. But if equal transit time has survived 80 years, the next big question must be, when a wrong model is believed so strongly, what makes changing it even harder? And why do so many people feel uncomfortable when told you've misunderstood lift? At this point, we touch the deepest part of the problem, not aerodynamics, but epistemology, the mental trap that makes people believe they understand even when they understand nothing. And that is what I warn about more strongly than anything else. The first principle is that you must not fool yourself, and you are the easiest person to fool. This isn't a funny quip. This is a serious warning from someone who spent his life shattering illusions the human mind builds. And lift is just one of countless examples. Because the problem is in misunderstanding. Misunderstanding can be corrected. The problem is thinking you understand correctly, and therefore losing the ability to learn anything new. This is the most dangerous mistake in science, more dangerous than knowing nothing. Equal transit time didn't kill aviation physics, it killed the learner's thinking. They believe they've understood because the explanation sounds so reasonable. So they stop asking questions, stop wondering, stop doubting. And science dies right there. Look at history to see how this thinking you understand has wrecked scientific thinking. Example 1. The 1913 Bohr model describing electrons orbiting the nucleus like planets around the sun. A beautiful image, simple, easy to draw, and completely wrong. Not slightly wrong, fundamentally wrong. Electrons don't follow definite orbits. They exist in orbitals, probability distributions, and quantum mechanics completely destroys that tiny planet picture. But because the model was so beautiful, it rooted itself in education for decades, even today. Many students still think electrons go round and round. The problem wasn't that the Bohr model failed. The problem was the strong belief that it was correct, which locked an entire generation's thinking. Example 2. Is light a wave or a particle? Throughout the 19th and early 20th centuries, the two sides fought as if only one could be right. Light is a wave. No, light is particles. No, light is a wave, but sometimes behaves like particles, all based on a wrong assumption that light must be one single thing. When the model becomes too simple, it makes people defend it like truth. Only when quantum mechanics arrived did we see that the wave-particle question was wrong. Light doesn't have to be one single thing. We are the ones trying to stuff it into a box. Wrong belief. Not the mistake itself is what paralyzes progress. This happens everywhere in classical physics. Centrifugal force treated as real, color treated as object property, the electron treated as tiny billiard ball, and lift treated as longer upper path. A world full of beautiful but wrong explanations. But the truth I've pointed out for a long time, you don't die from being wrong. You die from believing you're right when you're wrong. Belief creates blind spots. Blind spots kill curiosity. And when curiosity dies, science dies with it. Look back at equal transit time. It survives not because it's correct, but because it satisfies the human feeling of I get it now. Longer upper path. Air goes faster, pressure drops, no, lift. A beautiful, neat, palatable story, and worst of all, convincing enough to stop the learner from seeking more, thinking they understand, understanding nothing. I once said the hardest part of science isn't calculations or equations, but staying humble enough to see you still don't understand. The person who truly understands is the one who knows their model is just a model, and every model has limits. The person who thinks they understand is the one who clings to the model like truth, and therefore stops opening the door to reality. That is why every scientific advance begins with doubt, not satisfaction. We cannot learn what is right without destroying what is wrong, and we cannot destroy what is wrong without realizing we fooled ourselves. So to understand lift, you don't just need Newton or Bernoulli or circulation. You need the right attitude. Something doesn't add up. Let me check again. And that very attitude leads us to another realm of aerodynamics, the realm where equations become chaotic, where calculations become so difficult that humanity hasn't solved them in 200 years. A realm where, if you don't know it, you'll think we already understand flow. But if you do know it, you realize we've only stepped through the door. I'm talking about Navier-Stokes. After dismantling every misconception about lift, we hit the biggest wall in fluid physics, the wall that has stood tall for 2 centuries, challenging the greatest minds in human history, the Navier-Stokes equations. You might think that after Newton, Bernoulli, Prandtl, Kutter, Joukowsky, Kelvin, we have a relatively complete understanding of flow. But the truth is the opposite. Everything we've just explored is only the pleasant part of aerodynamics, the smooth part, the teachable part, the drawable on a blackboard part, the part airplanes rely on to fly in steady conditions. But real flow out there, it isn't smooth. It isn't gentle. It isn't obedient like the flow in textbooks. It is nonlinear, chaotic, turbulent, extremely sensitive to initial conditions. And the Navier-Stokes equations are the set that describes all that chaos. The story begins in 1822, when Claude Louis Navier added viscosity to the Euler equations by including the stress tensor. By 1845, George Gabriel Stokes completed the model, creating the system we now call Navier-Stokes. But unlike many beautiful equations in physics, Navier-Stokes is a mathematical monster, second-order nonlinear, tightly coupling velocity and pressure, capable of spontaneously generating chaos even from perfectly steady inputs. Just a tiny change in initial conditions. Just a tiny one. And the solution can explode like a flood. And from that arises the phenomenon every pilot knows, every aerodynamicist fears, and every mathematician agonizes over. Turbulence. Turbulence is Navier-Stokes going rogue. Chaotic flow rolls into large vortices. Then those vortices break into smaller ones, then smaller still, until energy dissipates at molecular scales. An energy cascade from large to small scales, described by Andrei Kolmogorov in 1941, but still not fully explained mathematically today. And this is where Navier-Stokes becomes literally mystical. No one knows for sure whether smooth solutions to these equations exist in all conditions, and if they do, whether they remain smooth forever. In 2000, the Clay Mathematical Institute declared one of the 7 Millennium Prize problems, proved that smooth 3D solutions of Navier-Stokes exist and are always bounded, or prove the opposite. Prize, $1 million USD. As of now, 2026, no one has solved it. Not Einstein, not me, not any leading contemporary mathematician. Navier-Stokes still stands there, challenging all of civilization. And the irony here is, we can fly without solving Navier-Stokes. What do aeronautical engineers use? Experiments, wind tunnels, real flight data, approximate models, and today, CFD numerical simulations from the 1980s to 2020 allow us to approximate Navier-Stokes solutions. But remember, CFD is not analytic solution. CFD divides space into millions of tiny cells and solves approximate equations with algorithms. It is not continuous. It is not perfect. It is not the true solution. It is only simulation. And sometimes, very often, CFD is wrong. Wrong at high angles of attack. Wrong in separation regions. Wrong in complex turbulent flows. Wrong in wake turbulence. Wrong in stall. CFD is a tremendous effort, but it doesn't replace the fact that we still don't fully understand turbulent flow. This may sound scary, but actually it is part of the beauty of science. The most beautiful thing about science is not knowing. Not fully understanding Navier-Stokes doesn't stop us from flying, doesn't stop us from designing safe airplanes, doesn't stop us from sending astronauts into space. Instead, it reminds us that our models are just models, and reality is always more complex than the models we create to comfort our minds. But this is also exactly why I want you to understand lift correctly. If you think lift is just Bernoulli, you'll think we already understand everything about flow. If you think lift is just Newton, you'll think we don't need Navier-Stokes. If you think lift is just circulation, you'll forget that circulation is the consequence of an entire foundational dynamic system. When you realize we still haven't solved the most basic equation describing flow 200 years after it was written, you become humble in the face of the truth that airplanes fly not because we've finished understanding aerodynamics, but because we know enough to work with reality. Even when theory is incomplete, airplanes fly because we rely on models that are good enough and accept the rest through experiments, testing, and engineering ingenuity. This is not a failure of science. This is science. But if Navier-Stokes is the biggest wall, then behind that wall is a door opening to an even more beautiful world, turbulence. The phenomenon that is both the obsession and endless inspiration of every fluid physicist. This is the moment we step into the realm where Navier-Stokes becomes most alive, the realm. So mesmerizingly beautiful, yet so chaotic that even the greatest minds have to pause. Turbulence. Turbulent flow. If lift is a miracle you can describe, then turbulence is a miracle you can only observe and marvel at. Turbulence is the most important, unsolved problem of classical physics. Not because it is abstract, but because it lies where human intuition completely surrenders. Everything you thought you knew about flow, smooth, continuous, stable, shatters when you enter turbulence. Imagine looking at the wake of an Airbus A380, the air torn into gigantic vortices, kilometers long, spiraling downward like two invisible dragons, then spontaneously breaking into thousands of smaller vortices, then millions even smaller, until they vanish at the molecular scale. That is not disorder. That is hidden order within chaos, a physical system operating by rules yet so complex that humans can never fully predict it. And it is this infinite cascade that Andrei Kolmogorov described in 1941. The Kolmogorov cascade, an energy cascade. Energy is transferred from large vortices, like the wake right behind the wing, to smaller ones, and smaller still, in an unending iterative process. From meter scales, centimeter scales, millimeter scales, micrometer scales, molecular scales. At each level, more swirling, more breakup, more energy transfer, until viscosity finally absorbs the energy at the smallest scale. A physical structure both powerful and exquisitely beautiful, yet impossible to compute exactly. And this is precisely what makes turbulence an analytically unsolvable problem, not because humans lack intelligence, but because the Navier-Stokes equations in turbulent regime become a non-linear labyrinth, where the tiniest perturbation breeds enormous chaos. I call turbulence the most important unsolved problem in classical physics, not because it gives mathematicians headaches, but because it is everywhere, in airflow over airplane wings, in wakes behind propellers, in river currents, in smoke rising from a candle, in towering cumulus clouds, in wind blowing through cities. Your universe is full of turbulence. You breathe turbulence. You live in turbulence, but you do not understand it. No one understands it. Even today, with supercomputers millions of times more powerful than those in the 1980s, we still cannot simulate turbulence from first principles with Navier-Stokes without approximations. CFD can try, but it can only approximate. It is not an analytic solution. It is not absolute truth. It is only a blurry picture of something too complex to be constrained by algorithms. But even though turbulence is uncomputable chaos, it still leaves characteristic signatures we can recognize. One of those signatures is the Kalman vortex street. When flow passes a cylindrical object, like a lamppost, a tower, or an antenna, it produces an alternating symmetric series of vortices, shedding left and right in turn. This is what makes power lines hum in the wind. Steel poles bend, bridges oscillate, and small aircraft shake when flying in the wake of a large one. And if you watch it through a high-speed camera, you see a staggeringly beautiful chain of vortices, a rhythmic spiral sequence, like nature's fingerprint. The interesting thing is, what you see in a Kalman vortex street behind a pole is exactly what happens in the wake of an Airbus A380, only differing in scale, speed, and energy. The Airbus generates vortices so powerful that the FAA requires 7 or 8 kilometers separation between an A380 and following aircraft to avoid being caught in the turbulence. A single large vortex from those enormous wings can roll long enough to flip a small airplane upside down in an instant. And all of this, from the cascade to the Kalman vortex street to wake turbulence, stems from the fact that real flow is never perfectly laminar. It always contains some turbulence, and that part is the heartbeat of aerodynamics. But do not be mistaken, turbulence is not just a nuisance. It is a sign of life in the flow. Without turbulence, there is no mixing of air, no efficient energy distribution, no natural flow. Nature uses turbulence as a tool, It is only humans who have not fully figured out how that tool works. And here is the beautiful part. Turbulence both destroys models and creates models. Chaotic yet ordered, disorganized yet governed by laws. Unpredictable in every detail, yet statistically predictable on the large scale. Nature does not care about simplicity. It only cares about truth. So after all this, how do airplanes fly in a world where flow is never simple? The answer is they fly because engineering does not need a complete analytic solution to Navier-Stokes. They fly because we observe turbulence, measure turbulence, understand the statistical laws of turbulence, even if we cannot solve it analytically. They fly because we accept that our models are imperfect, yet still good enough. And that brings us back to the most fundamental realization. Models are not reality. Models are only maps. Reality is always more complex than the map. And to close our long explanations, we must return to the foundational lesson of a world not made simple for your comfort. The world becomes simple when you observe it the right way. We are approaching the conclusion, the part where I want you to look back on the entire journey and realize something bigger than airplanes, bigger than lift, bigger than Navier-Stokes. Truth in science is always deeper, broader, and more beautiful than any simple story we tell ourselves. After traveling through all the deepest layers of aerodynamics, from boundary layers thin as paper to turbulence spanning kilometers, we return to one of the most foundational lessons I always try to remind everyone. Models are only maps, not the territory. We do not live in equations. We live in the real world. And every equation we create, from Newton to Bernoulli to Navier-Stokes, is only a clumsy attempt to describe a piece of reality. Airplanes fly not because we have understood the entire universe, but because we understand just enough to create temporary models that work. This leads to an important truth. The three models of lift, Newton, Bernoulli, circulation are all correct, and at the same time all incomplete. Newton correctly describes momentum change, but does not tell us why the airflow is deflected in that specific way. Bernoulli correctly describes the pressure-velocity relationship, but does not tell us why velocity is distributed that way. Circulation correctly describes velocity distribution in lift per span, but does not self-explain why circulation appears without the starting vortex. All of them are cross-sections of something larger, like three flashlights shining on the same gemstone. You see reflected light from three different angles, but the real gem is far larger than those three beams. We never know the truth. We only know approximate models of the truth, and those models get better over time. What we have about lift today is not ultimate truth. It is only a better model than the old one. And in science, better is absolute victory. When a new model explains more data, has fewer contradictions, predicts more strongly, it replaces the old. Not because the old was completely wrong, but because the old was less correct. Newton was correct for nearly 300 years until Einstein clarified it was only an approximation at low speeds. Bernoulli is correct in steady irrotational flows, but not in stall. Navier-Stokes is correct, but analytically unsolvable, and turbulence is correct, but unpredictable in every detail. No model is 100% correct, but all are correct within their own domains, and that is how real science operates. There is no final event. There is no final answer. Only models that improve, and when a better model appears, we use it without regretting the old one. Look at lift. The Bernoulli model is not wrong. It only describes the consequence, not the cause. The Newton model is not wrong. It only describes the effect, not the structure that produces the effect. The circulation model is not wrong. It only needs boundary layer, viscosity, starting vortex, quota condition to exist. All are approximations like every other model of the universe. If you think you have understood nature with one simple story, then you certainly have understood nothing. Nature is more complex, more beautiful, more subtle than any model humans have ever created. And here is what matters. Truth does not need to be simple to be correct. But models must be simple to be useful. Airplanes fly not because Navier-Stokes has been solved analytically. Airplanes fly not because humans fully understand turbulence. Airplanes fly because we have models correct enough to design wings, calculate lift, predict stall, understand wake, and use experiments to fill in the missing parts. We command the sky with incomplete maps, and that is the essence of experimental science. All of this leads us to a beautiful and honest realization. The universe does not need to be simple for us to understand. We need enough humility to accept its complexity. And when you look at an airplane flying through the sky, you do not just see lift, you are looking at a mental map patched together by generations of science, a map that is never complete, yet good enough to carry humans across oceans. This also brings us to the end, the part where I want you, the listener, to look back on the entire journey and ask yourself, in everything we have just explored, what is truly real? What is only a model? And what is still waiting for the next generation to understand more clearly? And then, after all the layers of models, equations, vortices, boundary layers, and the mysteries of turbulence, we return to the most familiar image, you sitting on an airplane at 35,000 feet, looking out the window, seeing the wings slice through thick white clouds like a knife cutting across a still lake. You look down at that tens of meters long piece of metal and see it gently rocking in the wind. Then you look at the clouds drifting beneath your feet. And if you have traveled with me through this entire journey, you suddenly realize a truth so strange it is hard to believe. Everything keeping you in the sky is just a layer of air, a few millimeters thick, not the entire atmosphere, not thousands of meters of air below, not anything majestic. It is precisely the thin layer of air right at the wing surface, where the no-slip condition forces the air to stand still at the surface, where the boundary layer begins forming the velocity gradient, where the flow decides to attach or separate, where stall begins when energy is insufficient, where the cutter condition forces the flow to leave the wing smoothly, where the starting vortex is born the instant the wing begins to move, where bound circulation suddenly appears and completely changes the velocity field, where streamline turning accelerates the upper flow and creates the low pressure region, where downwash forms and spreads kilometers behind like Newton's signature, where lift finally manifests as the inevitable consequence of that entire chain of causes. No slip boundary layer, cutter condition, starting vortex, jumperfork, circulation, downwash, nift. A beautiful, tight, precise chain of cause and effect. But if you only look at the airplane from the outside, you would never guess its sophistication. Nothing simple is happening. No longer air path. No curved wing automatically creates lift. No miraculous single Bernoulli equation. There is an entire tiny physical ecosystem operating on a layer of air a few millimeters thick, and that very thing creates the miracle of flight. You do not need to be a physicist to see how beautiful this is. Sometimes when I fly through the clouds, I look out at the wing. Just look and feel an indescribable awe, not because a hundreds of tons airplane still flies, but because I know it is flying thanks to the interaction between the wing and a layer of air so thin that if you stuck your hand out, you would not even feel its thickness. That thin layer of air is where all the complexity of Navier-Stokes, boundary layer, vortices, turbulence converges into a system so delicate that the slightest deviation can break it. Yet at the same time, it is stable enough that you can fly across oceans, drink coffee, take a long nap, without ever thinking you are living thanks to an almost invisible layer of air. And that is the beauty of physics. The real world is more complex than every story we have ever tried to build to simplify it. Airplanes do not fly because of one theory. Airplanes do not fly because of Bernoulli or Newton or Kutta-Joukowsky. Airplanes fly because nature operates according to laws we have only partially understood and only enough to exploit them. And when you understand this, you start to see the world with slightly different eyes. You no longer settle for answers that merely sound reasonable. You start asking, what is missing here? Is this really true? Where am I fooling myself? Because the most frightening thing is not knowing. The most frightening thing is thinking you know when you know nothing at all. And the most beautiful thing is that every time you shatter an illusion, the world becomes more complex, but also more beautiful. The next time you look out at the wing, remember that you are looking at a lesson in science, in humility, and in how the world really works. Nothing simple is happening. But precisely because it is not simple, it is beautiful. If this is something you once believed without ever checking, try looking. How many other things do you think you know but actually don't? If you want to continue exploring fascinating science stories in the Feynman style, remember to subscribe to the channel so you don't miss the next part. See you again on the journey to decode things that seem familiar, but turn out no one truly understands.